Okay, so we're looking at our different types of bonding. So we have ionic bonding, covalent bonding, and metallic bonding are all intramolecular. Means these are bonds between our elements that make up our molecules. So the ionic bonding is the transfer of electrons. So usually between metals and nonmetals. So if I have an electron on my one element, so potassium there has one electron, and then chlorine, which is my nonmetal, has 7 electrons. So now the potassium has one to give, the chlorine needs one, so it is going to transfer its electrons from where it has to there to make all the outer shells fill. So that's going to lead us to my potassium, which now has an empty outer shell. And since it's lost an electron, it gets a positive charge. So we put square brackets for positive charge. Right next to the chlorine, which has taken that electron. And we put square brackets because now that it's gained an electron, it has a negative charge. And we show them right next to each other with their charges because for ionic bonding, now these charges, they are super attracted to one another, and we form a huge ionic lattice because now to the next ions that are K plus and Cl minus, they're going to form there and they will stick together, and this is a very, very strong bond with a form of attraction. So for example, the next one, if I have magnesium is in group 2, so it has 2 electrons in the outer shell. And if I'm joining it with chlorine, which has 7, it's only missing 1. So that magnesium would give its 1 to the chlorine, but now there's another one, which means there has to be another chlorine which is missing 1. And then the magnesium is going to take and give it to the next one. So now for one magnesium, it means there are 2 chlorines that are taking those electrons. So when we draw our ionic bond, the magnesium still has lost both electrons, so it still has an empty outer shell. But now its square brackets, because it's lost 2, means its charge is now 2 plus. And the chlorine which has its 7 electrons, has still only gained 1 each. So its charge is still 1 minus because it still gained 1 electron. But there was 2 of them. So I can put a 2 in front of that chlorine to represent there's 2 of those. But that charge still remains as 1. And that charge is 2. Okay, so that's how we're going to represent ionic bonding. So then, covalent bonding is when electrons are shared. So when we have our sharing of electrons, that's usually between nonmetals. So for example, if I have a chlorine molecule like this, it has 7 electrons around it. So I can say there's 1, 2, 3, 4, 5, 6, 7. So we always go 1, 2, 3, 4 single electrons, and then we pair them, because this will tell us how many of these lone pairs of electrons we have. So chlorine has 1, 2, 3 lone pairs, and now it's missing 1 electron that it wants to share. So it can then share that with any other molecule that has 1 electron that it also wants to share. So for example, I can share it with hydrogen, which has 1 electron that it wants to share. So we draw these dot and cross diagrams to show the different electrons on the different atoms. So the hydrogen I gave a dot because the chlorine electrons I gave crosses. So you always need to represent them with different ones. And if you have 3 different types of atoms in there, you could do a cross, a solid dot, and then an open dot, like that, to represent the different electrons. So if I have another one, like this carbon, there I have 1, 2, 3, 4 electrons, because carbon is in group 14. So because it has 4 electrons, it now needs 4 electrons to become whole. So it could share those with maybe 4 hydrogens, for example. So then I can add hydrogen, which is going to share its electron, another hydrogen, which is going to share its electron, another one, and another one. Now those become bond pairs. So this molecule only has bond pairs in it, whereas this one has lone pairs and bond pairs. So if we look at different examples, now I have BF3, so boron with 3 fluorines attached to it. So if I look at boron, boron is in group 3. So I have boron, and it has 3 electrons next to it. So now it can make 3 pairs. Since there's 3 fluorines, each one of those is going to pair with the boron. So that's going to share its extra electron, and then fluorine still has its 3 lone pairs around it, because remember it still has 7. It's just shared its last one each with the boron. So there's our dot and cross diagram for BF3. But now, the thing that we can notice here is that boron only has 6 electrons around it now that it's whole. It's still missing a pair at the top. But that's okay, because sometimes we have exceptions to rules where we can have more electrons around than 8, or we can have less. So this one is one of those exceptions. If I look at the next one, I have CO2. So I know carbon has 4 electrons, okay? Oxygen is in group 16, so it has 1, 2, 3, 4, 5, 6 around it. So now oxygen is missing 2 each, and there's 2 of them. So each oxygen is going to need 2, and since carbon has 4, 2 of them are going to go to each oxygen on each side. So we're going to form what we call double bonds. So if I'm going to draw that, I have my carbon, and I have an oxygen, and I have another oxygen. And the carbon is sharing 2 electrons with each of those oxygens to become full. So I can say it shared 1, and then it shared the other. So there I have 2 bond pairs, and then oxygen still has its 2 lone pairs on each side. So then on this one it was a cross with a dot, cross with a dot, and then my 2 lone pairs. So each one of those is a bond pair. So that carbon is going to have 2 bonds with each oxygen, and that's how we get a double bond. So wherever we're drawing our dot and cross pairs, those represent a bond. So when we're writing it as a structural formula, that's what that looks like, because there's each of those bonds. We can represent them as a line. And then if I look at nitrogen here, N2, so there's 2 nitrogens. Nitrogen is in group 15. So that means it has 5 electrons around it. So now all singles plus 1 bonded means that's 1 lone pair. So now it's missing 3 of them. So if I want 2 of them together, they both have 5. That means that that has 3 to give, and that has 3 to give, to share with each other. So now all 3 of them can share, which means in the end, my nitrogen with my nitrogen means each one of those is going to share. And then we have the lone pair still on each side. So now, since it was sharing 1, 2, 3 pairs, it's now N with 3 bonds to N, and that's a triple bond. So you can have any amount of bonds as long as there is the correct number of electrons that are being shared with each other. So all you have to do when you're doing these is always look at how many of each thing is bonded, and it's always going to be that first thing bonded next to those others. So always start with that first atom that you have. See how many electrons does it have, and then look at what it's bonded with, how many electrons it has, and that will tell you how many single or double bonds or triple bonds it can make. So then our next kind of bonding that we also have, which is a type of covalent bonding, but it's a special kind of covalent bonding. If I have a dative or coordinate bond, so that means because we have lone pairs of electrons, sometimes that lone pair, because it's already 2 electrons, can give both electrons to something that is missing electrons. So usually if it's an ion or if it's one of those molecules like boron, which only has those 3 around the outside, it can get the extra pair from something that has a lone pair. So if I look at this one, this nitrogen has been bonded with 3 hydrogens. So that's NH3, ammonia, and it has 1 lone pair. But this hydrogen has already lost its electron. So this whole thing that's lost an electron has a positive charge. So it can then say, okay, it needs 2 electrons, and it can get both of the electrons from there to give to that one. So we can have that nitrogen bonded with its 3 hydrogens that it's already got. And then that last lone pair is going to share with the hydrogen that doesn't have it. So this bond, where there's 2 of the same, is now my dative or coordinate bond. Okay, and since this was missing an electron and it had a charge, it means this whole molecule is still missing an electron that would have been there from the hydrogen. So the whole thing now gets a positive charge. So this becomes NH4 plus, which now makes ammonium, because that was NH3 plus H plus to make NH4. So that represents a dative or coordinate bond. And if we want to draw that bond by showing a structural formula, we can say N with its 3 regular H's, but that last one that's taken both electrons, we draw an arrow instead of a line. It's an arrow from where there was the electrons to where it's giving the electrons over there. So that represents my dative bond, just like that represents over there. And you can sometimes have more than one dative bond in a molecule. So for example, my aluminium chloride with those 3 around there, aluminium is missing a pair over there. That aluminium is also missing a pair. So what can happen is the chlorine of one with lone pairs around it can give a pair to the aluminium that's missing. And the chlorine on the other aluminium over there can also give its pair to that aluminium that's missing. So we can form 2 dative bonds to join this molecule together, because you've got your aluminium with its chlorines and then that chlorine joins on to that aluminium with its other chlorines. So there's all the chlorines. So we're forming a dative bond over there from that chlorine and over there from that chlorine. So to draw it simply, we have aluminium with its chlorines, and the next aluminium with its chlorines, and a dative bond between the chlorine on the one giving its electrons to the aluminium over there, and that chlorine giving its electrons. So those over there are my 2 dative bonds. So that's how we would represent that molecule with 2 different bonds that are being shared. So just remember that whenever you see a lone pair giving both the electrons, that would represent a dative bond, and you can have more than one. So then that's also a covalent bond. So always just remember that. So there's ionic, then there's covalent or dative bonds, and then our last kind of bonding, metallic bonding. So metallic bonding is between metals, and the metals lose the electrons, and electrons always become delocalized. So whatever metal I have, this is between its own atoms. So if I'm dealing with magnesium, these are all going to be magnesium ions that have lost their electrons, or copper, or zinc, or anything like that. So it loses electrons and it becomes positive ions. So those electrons then become free. So if it loses 1 electron, it gets a 1+ charge, and there's 1 free electron per atom. If it loses 2 electrons, then it becomes a 2+ charge, and it's lost 2 electrons per atom. And now those ions that have lost all their charges form a regular arrangement in a lattice with delocalized electrons running through, and those are free to move, and that's what gives metals their properties. But it also holds all those ions together, because negative electrons are strongly attracted to positive ions, and that's why you have this strong lattice, and that's why metals are so strong, because of the metallic bonding within them. So whenever you're asked to represent metallic bonding, you will always just draw ions, depending on the metal, as to how many charges, with free electrons holding them together in this type of lattice. And that is metallic bonding. So whenever you're asked about metals and why their melting points are so high, it would be because that metallic bonding is very, very strong.